What if I told you the strongest clue for alien life might arrive as a three-letter chemical in a thin beam of light that traveled more than 100 years to reach us? And we could spot it from a dataset you can download in seconds? Right now, as you watch this, telescopes are doing something that sounds impossible. They're splitting starlight into thousands of colors, like a cosmic barcode, then hunting for tiny missing slivers of light that only appear when a molecule in an alien atmosphere steals that exact color. And the wild part is the signal we're chasing can be smaller than a 1% dip in a star's brightness, yet it can still tell us what an unseen world is made of. Hold on to that thought, because later I'm going to name the specific three-letter molecule that's causing real debate, and why, if it ever shows up on the right kind of planet, it won't just be interesting. It'll be the kind of clue that forces a courtroom-style argument about life in the universe. Because here's what defies common sense. We're trying to diagnose a planet we can't see directly by reading the smell of its air from light that started its journey before your phone, your laptop, and basically modern life existed. If you want a visual you can actually feel, imagine trying to identify a single candle on the moon from Earth. While someone shakes your telescope and you're not allowed to look at the candle, only the candle's scent. That's the game, except the candle is a planet, the scent is chemistry, and the shaking is everything from star spots to instrument noise to the planet's own clouds. And yet, somehow, we're doing it. We've now confirmed over 5,000 exoplanets. NASA's Exoplanet Archive tracks the count. And the deeper lesson from the planet-hunting era is even bigger than any individual world. Planets are not rare trophies. They're the default, which means habitable real estate might be common too. Not guaranteed, not promised, but common enough that the question, "Are we alone?" stops being poetry and starts becoming a measurement problem. Now stack the impossible facts on top of each other. 1. Many of these planets are so far away that if you tried to visit at the speed of our fastest probes, you'd be planning a trip longer than recorded human history. 2. The best atmospheric signals we get from some planets are basically a few dozen meaningful data points buried in a messy spectrum. 3. Those few dozen points might still contain the fingerprints of water vapor, carbon chemistry, and gases that should not coexist unless something is constantly making them. That last part is what makes scientists sit up straight, because life, at least life we recognize, does two big things to a planet. It moves energy around, and it changes chemistry in a way the planet can't maintain on its own. Earth is the poster child. Oxygen is reactive. Left alone, oxygen should get eaten by rocks and gases. The reason we have so much oxygen in our air is that biology keeps refilling the tank. Earth's atmosphere is not a quiet equilibrium. It's a machine that's being operated. So the astrobiology idea sounds straightforward. Find a planet with the right temperature range for liquid water, then look for atmospheric gases that suggest biology. But then reality hits. Planets are master illusionists. Volcanoes can produce methane. Sunlight can split water and leave oxygen behind. A planet could look alive while being completely sterile, just chemically weird. This is why serious scientists don't want one magic molecule. They want a case, a pattern, an imbalance that's hard to fake. And this is where things get strange. For a long time, exoplanets were basically dots. We could detect their presence, weigh them, estimate their sizes, maybe guess their densities. But life, that felt like a bridge too far. Then the 2020s changed the hardware and the math. Observations got more stable, analysis got more rigorous, and as the field headed into the mid-2020s, into the 2026 era of planning and instrument upgrades, the question shifted from, can we detect atmospheres, to, can we cross-examine atmospheres? Here's the trick that makes this possible, and it's beautifully simple. When a planet passes in front of its star, transits, most of the star's light is blocked by the planet's disk, but a tiny fraction filters through the planet's atmosphere. That atmosphere acts like a thin, colored lens. Molecules absorb specific wavelengths. So when you compare the star's spectrum during transit to the star's spectrum outside transit, you get tiny notches, molecular bite marks. That pattern is the planet's atmospheric ID card. But you might be thinking, okay, so you see a notch. How do you go from notch to aliens without embarrassing yourself in front of the entire scientific community? Exactly. This is why the field is obsessed with false positives. So instead of searching for one glowing neon sign that says, life here, scientists are building what I'll call the habitability stack. Context plus chemistry plus persistence. What kind of star is it? How violent are its flares? Can the planet even hold on to an atmosphere? Is the planet likely rocky, or is it a mini Neptune with a thick hydrogen envelope that crushes any Earth-like assumptions? Does the chemistry make sense together, or does it look like a lab accident caused by radiation? If you want to keep up with what's coming next in this story, because the next part is where it turns into a real mystery, subscribe. What I'm about to reveal is the three-path strategy scientists are using right now. One path is deep space spectroscopy. One path is right here in our solar system, and one path is basically a philosophical knife fight over what counts as evidence. Let's play. Detective in order. In 1995, Michel Mayor and Didier Queloz announced the first confirmed exoplanet around a sun-like star, 51 Pegasi b. That moment mattered because it shattered the old, comfortable assumption that our solar system might be special. Suddenly, the universe wasn't just stars. It was stars with companions, lots of them. Then came the planet census era. Kepler, launched in 2009, watched star after star after star, looking for those tiny dips in brightness that scream, planet crossing. By the time the dust settled, Kepler didn't just give us a list, it gave us statistics. Small planets are common. Multi-planet systems are common. The galaxy is not empty, it's crowded. And once you know planets are common, your brain naturally asks the next question. So, what are they like? Early atmospheric studies with telescopes like Hubble were a start, but it was like trying to read a street sign through fog. At night, while running, you'd get hints. A bump here, a wiggle there. Enough to be tantalizing, not enough to be sure. Then the 2020s arrive with a serious upgrade, the James Webb Space Telescope. JWST's job isn't find planets so much as interrogate planets. Measure the chemistry of worlds light years away through precise spectroscopy. And as teams began publishing atmospheric constraints and detections on different kinds of exoplanets, something became obvious. We're finally transitioning from planet discovery to planet diagnosis. At the exact same time, our own solar system started acting suspicious, in the best possible way. Because if exoplanets are the far frontier, the solar system is the close-up crime scene. Take Enceladus, a small moon of Saturn. Cassini observed it venting material into space. Plumes of water vapor and ice grains blasting out from fractures near its south pole. That's not a metaphor. That's a moon spraying its insides into space like a cosmic geyser. Later, analyses indicated salts and organic molecules, ingredients that make astrobiologists go quiet for a second. Because quiet is what you do when the universe hands you something too convenient to trust. It's not proof of life, it's proof of opportunity. And here comes a cliffhanger that splits the hunt into two opposite strategies. Strategy 1. Hunt atmospheres far away, worlds we will never touch, at least not soon, by reading their light like a barcode. Strategy 2. Hunt ocean worlds nearby, places like Enceladus and Europa, where the solar system might literally offer us samples, not just photons, actual material. So which one finds life first? Now we hit the reveal, the part where the chaos becomes a plan. Scientists believe we're closer than ever because we're no longer betting everything on a single miracle signal. We're building a case with three independent lines of evidence. Path 1. Atmospheric fingerprints on exoplanets. During transits, we can infer molecules, water vapor, carbon dioxide, methane, and other species depending on the world and the data quality. But the goal isn't spot one molecule. The goal is to find chemical imbalance, pairs or networks of gases that shouldn't calmly coexist. Think of a planet's atmosphere like a bathtub. If the drain is open and you still see the water level staying high, something is running the faucet. On Earth, biology is a major faucet. And now we get to the three-letter molecule I teased, DMS, dimethyl sulfide. On Earth, DMS is strongly associated with biological activity, particularly ocean ecosystems. So if scientists saw a strong, repeatable DMS signal on a temperate exoplanet with other supportive context, signs of an ocean-friendly temperature range, complementary chemistry, and a plausible atmospheric structure, you'd understand why people would lose their minds. But stay with me here. DMS detected is not aliens confirmed. It would be a clue, an intense one, that demands follow-up, repeat observations, and ruthless attempts to kill the hypothesis with alternative explanations. Science doesn't crown kings. It cross-examines suspects. Path 2. Ocean worlds you can sample. Enceladus is basically doing our drilling for us. If you can fly a probe through a plume and analyze the chemistry, you're no longer guessing from far away. You're doing forensics. Salts imply liquid water interacting with rock. Organics imply complexity. Certain patterns, especially in the distribution of organics or isotopic ratios, could be suggestive in the way fingerprints are suggestive. Not a confession, but evidence. Path 3. The context stack, habitability plus false positive testing. This is the part that makes 2026 feel like a turning point in vibe, even if the breakthrough result could come any year. The field is maturing into adversarial verification, better stellar monitoring, better models for photochemistry, better lab experiments that simulate exotic atmospheres, more independent teams reanalyzing the same data sets. The goal is to make claims that survive contact with skeptics. Researchers like Sarah Seeger have spent years pushing biosignature frameworks, how to evaluate possible life signals without fooling ourselves. And scientists like Niku Madhusudan have argued in published work that certain sub-Neptune planets could be Hycean candidates, worlds with potential global oceans under hydrogen-rich atmospheres. That idea is debated, and it should be, because debate is what hardens a claim into knowledge. So yes, the answer is satisfying. We have tools, targets, and strategies. We can finally build a case instead of telling a story, but it immediately raises the question that keeps scientists awake. What if nature can fake the same lifelike signals without life? Record scratch, plot twist. False positives are not a footnote. They're the boss battle. Methane can come from geology. Oxygen can accumulate if intense. UV radiation splits water and hydrogen escapes to space, leaving oxygen behind. Some worlds might be chemically extreme in ways Earth never trained our intuition for. Even sulfur chemistry, the stuff that makes DMS interesting, could have pathways we haven't fully mapped under alien conditions. And then there's the star problem. Many of the most tempting Earth-size in the habitable zone targets orbit red dwarf stars because red dwarfs are small, so a planet blocks a larger fraction of their light, making transits easier to detect. But red dwarfs can be violent. Flares, particle storms, UV spikes, that can strip atmospheres or manufacture confusing chemistry. A planet might look alive in spectra while actually being chemically torched by its star. And there's another uncomfortable layer. The signal is tiny, and humans are pattern-finding machines. Different analysis choices, how you correct for instrument systematics, how you model clouds, how you handle stellar contamination, can shift conclusions. That's why you'll see scientific disagreements that look like drama, reanalyses, competing models, not confirmed, needs more data, could be noise. It's not chaos, it's quality control. So here's the uncomfortable truth. The closer we get to finding life, the more we're forced to define what evidence even means. And weirdly, that's what should make you optimistic, because the field is learning to stop fooling itself. Now, I genuinely want to know what you think, because this isn't just a trivia question. It's a prediction about how discovery actually happens. If we find alien life first, do you think it'll be a biosignature-style clue in an exoplanet atmosphere? Something like a DMS-type signal that survives repeated tests, microbes or biochemistry in an ocean world plume like Enceladus or Europa? Or 3. Something weirder. Life with chemistry that doesn't look like Earth at all, so we almost miss it because we weren't looking for the right pattern. Drop your pick and your reasoning. I'm reading the comments, especially the ones that argue against the obvious answer, because this matters for all of us for a reason bigger than, are we alone? If we detect life elsewhere, even microbial life, it tells us biology isn't a one-off cosmic fluke. It's a process the universe can run more than once. That would hit biology like an earthquake. What's universal? What's Earth-specific? What's required? What's optional? It would reshape geology too, because we'd be forced to understand how living chemistry interacts with oceans, rocks, and atmospheres across different worlds. Chemistry would get a new playground of reactions and pathways. And yeah, philosophy would have to sit down and drink water, because life stops being a local story. The future directions are getting sharper, not fuzzier, more observing time on the best targets to see whether signals persist. Better monitoring of stars so we can subtract their chaos, lab experiments to map out false positives, and mission designs focused on sampling, because nothing beats touching the evidence. So here's the hopeful part. The uncertainty isn't failure, it's the scientific method doing its job in real time. We're learning how to avoid being fooled by noise and by nature's own tricks. We're learning what to measure next. And every year the instruments improve, the models get stricter, and the debate gets more precise. We're not waiting for one perfect headline. We're assembling a verdict, but this isn't the only way alien life could reveal itself. Next, I want to dig into how technosignatures, signs of technology, might actually be easier to spot than microbes, why rogue planets drifting between stars could hide warm oceans in the dark, and the wild idea that some biosignatures might come from chemistry we haven't even discovered yet. Thanks for watching. The universe has been doing chemistry for 13.8 billion years, and we're finally learning how to read the recipe. Keep looking up, keep thinking big, and I'll see you in the next one.